Hello everyone, welcome to the 8th video of 10 AP Physics 1 summaries. Today we'll be looking at the electric charge and electric force unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I will include timestamps in the comments for each topic. Let's get started. You've definitely heard of electric charge before, whether it's relating to batteries or static shock, but today we're going to look at electric concepts through a more rigorous lens. We're going to define what charge is and how it affects objects' behavior. This video will give context on the foundations of charge, especially on an atomic level. The first thing to note is that an object's total charge is the sum of the charges of the elementary particles present. Protons and electrons have equal and opposite charge, so any object's total charge is the sum of discrete integer multiples of elementary charges. Charge is based on the composition of a material, meaning the ratio of protons to electrons that make it up. Electrons have the ability to move and flow, so their movement can change total charge because it changes the relative quantities. Charge is measured in coulombs, and we will talk more on this later because the derivation of this unit is a little bit funky. Here we can see the charge and mass of the elementary particles, protons, neutrons, and electrons. As you can see, protons and neutrons have equal mass, while electrons are far smaller. Electrons and protons have equal and opposite charge, while neutrons have no charge. Remember that elementary charges cancel each other out by neutralizing each other's charge. That means that if you have equal quantities of protons and electrons evenly dispersed, no matter how many charges are present total, there will be no net charge. The charge of one electron is called the constant E with a little negative sign, and protons can be shown as either a little e with a plus sign or a p with a plus sign. Speaking of coulombs, there are 6.241 times 10 to the 18 electrons in 1 coulomb of charge. In questions on this topic, you will probably be working with single-digit quantities of elementary particle charges or entire coulombs, but you will not be going between the two. Just to reinforce an essential idea, if we have a particle that has 5 neutrons, 4 protons, and 2 electrons, what is its charge? First, neutrons have no charge, so we can rule this out as extraneous information. Now let's look for the net charge. The 2 electrons will cancel out 2 of the protons, so we are left with a net charge of positive 2. You can even see this in the name of the particle itself. Key takeaway: net charge follows the same principles of other net quantities. Let's go over the basics of electric interactions so we can understand how an object acquires a net charge. Neutrality is a key vocab term, but it's very simple. It is a special case of net charge in which the positive charge present equals the negative charge present. Remember that just because an object is neutral, that does not mean that it will not have any electric interactions. It just means that by itself, there is no imbalance of charge. It can still interact with other objects if they are charged. So, electrostatic interactions are pretty straightforward. The main idea of electric interactions is that like charges repel, while unlike charges attract. Objects become charged when they gain or lose an electron so that they are no longer neutral and there is an imbalance. Charging changes the net charge an object has. The first way of charging you will encounter in Physics 1 is friction. We see this in the experiment of rubbing a balloon on hair, which creates an attraction between the two. In this situation, you are stripping your hair of electrons that are sticking to the balloon instead. You are creating a charge imbalance, which causes an electric force. The second way is conduction. 2 conductors with a different net charge are touched together, and the electrons flow until the net charge on both is equal. Note that the net charge does not have to be neutral on both objects, just equal. Think of creating equal ratios of positive and negative charges on both objects after the conductive charging is done. At the end, both conductors have a ratio of 2 electrons to 1 proton in this example. The third way of charging is induction. Without contact, a charged object is brought towards another object, which causes the unlike charges to come towards the object and the like charges to be repelled away. This polarizes the other object. I'm going to show you these types of charging using a PhET simulation that I tried and recorded called Balloons and Static Electricity. I would highly recommend this resource to explore electrostatic force and charging yourself. We first see the balloon rubbed onto the wool sweater and charging through friction. By picking up the electrons on the sweater, the balloon gets a negative charge while the sweater is left with a positive charge. When released at a distance, the negatively charged balloon is attracted to the oppositely charged sweater. Then when the charged balloon is held against a neutral wall, inductive charge happens. The electrons in the wall are repelled by the balloon because they can move while the red protons are left behind. The force moving the balloon here is electric force, and it follows a similar form to the gravitation equation we saw earlier in physics. It is proportional to the product of the charges and inversely proportional to the square of the distance, and it has some constant as a coefficient. We are calling the elementary charge E. If we have two electrons on the bottom left at a distance r, they each exert an electric force of k times E squared over r squared on each other, and they will repel. On the right, we have 3 electrons and 1 proton. Assuming the 3 electrons are bound together, we have an electric force of k times 1 positive E times 3 negative E over r squared. This is 3 times the electric force on the left as shown by the vectors, so let's test our knowledge. So we have a situation with 3 positively charged particles. We know that they all repel because they all have the same charge. We know that net electric force on the center particle equals 0. What is the value of y over x? What is the value of these differences, the ratio? So if we're looking for the distances and we know that the net force on this is 0, we know that the forces exerted on it cancel out. And the only 2 forces exerted on it are the one from this particle and the one from this particle. Now these 2 outside particles have an electric interaction of their own, but it does not affect the center particle. So let's start labeling these F1, F2, and identifying the equation that we're working with here, which is F equals K Q1 Q2 over R squared. If F1 and F2 cancel out, then they have to be equal. So we're going to have 2 different versions of this equation. K, and then what are the 2 charges in this relationship? They are 2Q and regular Q over the distance is x squared equals this relationship, which is K Q dot 3Q over y squared. After some quick algebraic manipulation, we can see that a lot of these values actually just cancel out pretty easily, and we're left with, after cross multiplying, 2y squared equals 3x squared. And we're looking for this ratio, so then we can find that y squared over x squared equals 3 over 2. So y over x equals radical 3 over 2. So this is a good sample of the type of questions you're going to face on this topic. They're not that heavy lifting when we're actually talking about finding really crazy physics values. It's more just making sure that you can understand the essential relationships in equations like these. Be aware that electromagnetism is one of the fundamental interactions we mentioned in an earlier video. It determines many of the interactions between objects that we see every day. Electric forces are some of the forces that contribute to basic atomic and molecular formation. We are simplifying crazy amounts of tiny electric interactions when we talk about contact forces, because we are assigning macroscopic observations and relationships that result from these fundamental relationships. As our last major concept, charge is conserved. This will come up much more in our next unit, but the net charge of a closed system is conserved no matter what movement occurs between charges inside the system. Okay, we are done. In my next video, we will be moving on to Content Area 9, Direct Current Circuits. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.